happy, but
Just another one again.
Let me see if it's the same one. So you're now live. You're broadcasting on YouTube. Watch stream. I want to see. Watch stream. It's live. Yeah. Shoot. Let me see if it's the same one. I better mute. You're broadcasting on YouTube. Watch stream. Let's see. It's live. Yeah. Shoot. We've got a delay, so.
Audio delay. Yeah, I think I can hear what you were saying 10 seconds ago.
Yeah.
That's just the phone delay, though. It should be unrelated.
Well, there's both because I have my speakers still on.
It might go away once we switch to just one.
Yeah. Okay.
The noise canceling probably works better.
Yeah. Now here's the new link. I don't know if it's the same one.
That is indeed the same one. Okay, I'll try joining.
All right.
It says Daryl Richter's room offline. Hang tight. Daryl Richter will be here soon.
What the hell? All right, I'll generate new link. I can do that. So let's try this one. Great.
That's the same link.
Oh, is it? I clicked generate new link. All right, generate new link. Show my link.
Maybe it always generates the same new link.
No,
now it says, this link has been expired by the host.
Okay.
There's a new one. Join the stream. Okay, so maybe you just didn't copy in the second one, right?
Yeah, it's possible.
Try copy and pasting again. Yeah, this one's different. Okay. I'll type this into my computer.
I think this is not going to be the right link that I see.
I can see it.
Oh, I can. Okay, here we go. Add to scene. Oh man, look at that. I think we can even go like.
Peter, can you hear me?
I can, yes.
Is your audio muted, perhaps?
It is. What is it? Join? No.
There you go. Right, I'm hanging up the phone.
Yeah. All right, wait. I guess I gotta turn. Yeah. Shoot. Now, I guess I gotta turn. Oh, there you go. Shoot. And now let's see if you're on, but you're not. Oh, there you go.
This is the delay.
And now let's see if you're on, but you're not.
Or you could just.
Oh, now you can see my wife in the background.
No, I'm not here. Bye.
I don't know how I'm gonna hear because I can't. It's echoing, and it's not broadcasting you. Oh, wait. I know why. I think. Shoot. Huh. All right, I can hear you now.
Oh yeah.
Yeah, but now my camera is off. All right. Yeah. Now my camera is off. All right. Yeah. Now my camera is off. All right. All right. Now, okay, good, good. But now I don't think, see, you're not streaming to the stream right now, so I gotta figure that out. Yeah. This is, I believe, where it is. Yeah, that's because I accidentally deleted myself. All right. All right. This one. That's me. Now add to scene. Now I don't know why. But I don't know. Oh, okay. Hang on. I saw a button. There was a button there. Send to stream.
Oh well, your stream moved. Yep, there we are. I can see me now.
Oh.
All right, you did it. Well done.
Okay. Now our only problem is this is the wrong link that I didn't send out the link.
Where did you send the link to, or like where is that posted?
I posted it on the LinkedIn.
LinkedIn?
Yeah. Hang on.
Okay.
I'm trying to get it so there's such a delay. There's such a lag.
Yeah, how bad's the lag? What do you think? Well, there's going to be a lag if we're looking at the stream output, but I think that's fine. Like we just basically shouldn't be looking at that. Are you talking about lag like come from me, like just hearing me?
Yeah.
Hmm.
I think I hear you right away. Yeah. I think it's fine. You can hear me
Okay.
right now, right?
Yeah. Yeah,
Okay.
I don't experience any delay from you, so
See, I'm hearing myself.
yeah.
I'm hearing
Yeah,
myself
I
again.
don't experience any delay from you, so yeah, there's a delay when it gets to the stream. They've got to do the 4-second delay.
See, I'm hearing myself. Got it. Got it.
But I think that's fine. That's just going to be
All right.
that's
So
what we
I
expected,
just
I
have
think.
to stop the stream.
What?
I just have to stop listening to the stream. I had the stream open, and that's
Oh no, yeah. Don't listen to the stream. Just listen to the what this here. Yeah.
yeah. Now
You
the
just
only
got
thing,
like
I mean,
you just got all the sources coming in at you. You had like your microphones. You have two
I did.
cameras. You're like,
But now you're in the
living in a.
stream because it's funny when I look at the stream output, I can't see you. I can only see me.
That's true. I can't see me anymore either. I saw me for a while, and then it stopped. Maybe take me off the stream and put me on again. That seemed to work for you. I don't know
Yeah.
what you did there exactly, but
There's this add to scene thing.
Yeah, that's probably it. You can probably even like adjust the sizing on the scene, stuff like that.
Yeah. I'm just
Yeah.
trying to. I'm gonna have us. Okay,
So I'm planning on doing a screen share for most of this, by the way.
okay, and you're supposed to be able to do that.
Yeah, I tested it out on the previous link and it seemed okay.
Okay, now our only. I don't. Shoot, I don't know what to do about this. That it's at the wrong link.
Well, just send out a new link on all the
Yeah.
places where you
Yeah.
announced it.
Yeah.
Put it in Urbit chat
So I
too, and maybe
scheduled the
Twitter.
thing. I scheduled the thing, and I thought I would start that, but I guess I can't do that because I'm starting it from this Lightroom thing. Like if I do it from YouTube, I can't invite you. It's this light
Wow.
stream thing that lets me have two people at once.
Okay.
So yeah, let me get the link. Where is the link? What is this? Come on, YouTube. I almost did this on Twitch. And I actually, in retrospect, it probably would have been easier. Oh, wait. Oh, okay. Wait. This is live now. Darn it. Yeah, it's a different link, though. All right. Let me.
Sorry, I spaced out there for a minute.
No worries. I'm just trying to update the link everywhere. Come on. I said edit. Oh, is it not going to let... Oh, wait. Oh, I'm in the wrong freaking one. See, when you do things in a hurry, man, it's... Come on. Let me do it in Urbit too. Where's Urbit help? Uh, all right. Can you hear me?
Oh, hello. There you are.
There I am. Oh man.
All right. What happened there?
It just disconnected somehow.
Mm.
I don't know why.
This is a nightmare, man.
Yeah, I guess, this cutting edge technology stuff,
Have you seen that episode of Silicon Valley? That clip
No.
where they try to use this new, holographic teleconferencing thing, and it doesn't work, and so they fall back to Skype, and then that doesn't work, and they fall back to a cell phone, and that doesn't work.
All right.
Like,
And this is so weird. Every time I have to take off and then add back into the scene, and then all right.
You should just drag yourself around the screen like in a circle.
All right. So we should be live now. But now the interesting thing will be, is it a different URL?
Not the one that you just sent out.
I don't know.
You sure about that? Let me check the YouTube link again, because I suspect it just came back up. Like that's what it seemed like just now. Like I'd gone to the YouTube link that you'd sent me a few minutes ago, and it worked. Like it came back online. Yeah, it says live chat. Well, it's loading. I'm trying on my phone because I don't actually have the link on here. Can you send me the link?
The YouTube link that I pasted?
Yeah. Let me send it in this chat here.
Oh, yeah.
Well, it's like spinning on my phone, but that doesn't really mean anything.
We've got at least one person. We've got at least one person.
All right. No, this is working for me. Yeah, it's the same link. The V equals ORWEZ. All right, we got a couple of people. All right, cool. This is the obligatory "Can you hear me now?" section of the show. Cool.
All right.
Well, should we get started then?
Yeah, I think we can. Let me. We got lots. Look, we've got lots.
We got a full crowd.
Hopefully, everybody who was on the actual meetup itself. Wait a second. I don't want this camera. I want that camera.
Got to get your good side.
Yeah. Look at that. I'm like changing camera. I mean, I'm like going to be a video producer now. All right. So
we're going to do an instant replay.
Welcome, everyone. In the upper left there. All right. Is that right? In the actual, I don't know whether we're reversed or not, but this is Winter. You may have seen me around Urbit. I've been around Urbit for a while, since like 2016, actually. I've been having a lot of fun with it, since you couldn't do anything with it in 2016, literally almost. But it's been great, and it's been an honor to be involved in it all this time. I am one of those. I know people were talking in one of the chat rooms the other day.
We lost your video there.
Oh, really?
Yeah,
Damn it.
we can only get your bad side apparently. When you switch to
No,
the good
no,
side,
no.
it
I'm
just
going to
goes
turn it
blank.
on. I'm going to turn it on. I think I figured out how to do this
Thank you,
stuff.
people in the chat, for pointing that out. I didn't notice.
I will eventually get the hang of Lightstream.
I don't think I will. I don't think I'll ever figure this out.
Come on.
It's above my pay grade.
That's the wrong one. This is the right one.
Nah.
Add to scene. Oh, come on. Do not do this to me. All right.
we spent half an hour getting this right before this.
I know.
You wouldn't believe.
Well, I think I'm going to have to stick with the side view.
Yeah. You might want to put me back in the scene too.
Oh, you're out again?
I mean, I can just be a disembodied voice. It's fine. You can find pictures of my face on the internet if you really want.
This thing is...
No, we're good now. We're good now. All right. What were you saying? You've been on Urbit since 2016.
2016. It was funny. Some people... Oh, look at that. It's...
Just don't touch it. Don't touch it. It's fine. Let's just plow ahead.
All right. So it was funny because some of the people were talking on one of the chats the other day, like, "Oh, Urbit's all young people. There's no boomers involved with Urbit." And I was like, "Well, I'm almost a boomer. I'm year zero of Gen X. So yeah, I've been doing this a long time. First coded in C on Unix in 1977. So that's been a while. But Urbit's been great, and it's really one of the few things that excites me about technology today. After all these years, it's a very exciting thing. I think technology is kind of in a real lull, and this is, to me, this is the beginning of the next leap forward. So that's why I'm involved. I'm really excited this evening to have Ted here, or Rovnys, or Rovnys. I don't know how to pronounce
in the vernacular we say rovnys. You know, it really probably should be rovnys if we were sticking to the
real pronunciation.
Yeah, but you know, at Urbit we prefer convenience over pedantry whenever we can.
All right, so this is our first, Urbit in the time of coronavirus, virtual meetings.
Yeah.
If you are anywhere close to the Philadelphia area, we are going to be resuming live in-face get-togethers. Hopefully, I guess it looks like maybe not next month, but in May. You're always welcome. We've had a couple of good turnouts, so we're hoping to get some good traction going on here. But without further ado, I'm going to go to Rovnys and let him talk about the event log and nock. I'm going to make you bigger.
All right. Sounds good. Thanks. And I didn't realize that you'd written code in Unix in 1977. You know, they're actually, the number of programmers has been growing for a long time, doubling at a rate a little slower than viral cases, I think. But
yeah,
it's been doubling for a long time, and so it's actually pretty rare to meet a programmer who has that kind of experience. So it's pretty cool.
Yeah, I did a lot of mainframe as well, believe it or not, for many years. So,
well, I'm glad to see that you're interested in Urbit, because it kind of validates some of the claims that we make, I think.
Yeah.
It's actually, there does seem to be a kind of bimodal distribution of people who are interested in Urbit, where it's, and this has been observed before, but it's often like really new programmers who are very green and very experienced programmers. And so there's, for some reason, the middle tier of experience isn't as interested. I don't know why. All right, so I'm actually, can you guys see these, see what's on the screen here? You read everything?
Let me see. I might need to add that to the scene. Hang on. Let me try.
All right. Oh, the screen share. Okay, it's a separate
I
picture.
think it's a separate thing. So let's.
All
We
right.
haven't been all that successful with this so far, but
Yeah. I just switched
and
back.
now I'm going to send it to live.
Okay.
Maybe it's too big though. Is it? Is it too big or?
Like the font size. Or what?
Uh-oh. I
Okay.
think
While you figure out the
your screen.
streaming stuff, I'll just rant a little bit, which is kind of my plan anyway. So the yeah, so I thanks for having me on here. I was actually going to drive up to Philly for this, and I was thinking about swinging by New York. I'm in Virginia right now, and but decided against it um, for because plague, and so I'm glad we're having at least some success with AV here. The anyway, thanks for having me on, and yeah, I decided I was going to talk about nock and the event log, which are, I mean, they're technical subjects, but they're really core to what's unusual about Urbit, and I think we probably just don't really talk about them enough. Um, so this will be a technical discussion, but yeah, say something on the chat if I say something that you guys have trouble. You know, if I say something that is just total gibberish, it's always a risk. Um, and but I'll try to keep it sort of to not require too much background.
Why
So
is your screen? Your screen is supposed to be on the top, but oh no, wait. This is the weird thing. Let me try it down here.
yeah,
I,
all right. Well, keep trying. I can keep talking. So
all right.
let me know when you got it. But then I'll just keep ranting. The so Urbit is a personal server, as we say a lot, and it's implemented as a virtual machine. So it's a program you run on some other operating system. Right now, you can run it on top of Linux or on top of Mac OS, and we'll eventually get it running on Windows and other things. But the uh, but the idea is that Urbit treats the operating system, the host operating system that it's running on top of, as basically just like a hardware abstraction layer, um, and it doesn't. And so the idea is that all of the sort of user-facing software that you want to do, just about all of it, you want to run in Urbit. Um, and there are probably a few things that you want to run outside of it, like video conferencing, actually, although we've been talking about integrating Jitsi, an open source video conferencing suite, into Urbit, which I think we will do. But in general, you know, Urbit is this world that you live in digitally, right? It's got file systems. You can store all your files and data. You can install programs into it. You can chat with other people. You can share files. You know, various kind of productivity apps that we don't have yet, but we would love to have, like calendars and things like that. You can publish, do blog posting, that kind of stuff. And in general, sort of like all the day-to-day use cases of a computer, all the like, just for personal computing, right? Like, what is it? The stuff that we're trying to track, the rules that we want our computer to maintain for us about how to maintain our digital lives. That's what Urbit is for. And so the overall idea there is you want some system uh, that's as simple as possible and as abstract as possible in a way that makes it so that it's going to continue to work very far into the future. And it's got to be a virtual machine because you got to be able to move it from one physical machine to another machine. Right? So it's like you're taking this whole kind of, you know, virtual operating system and running it in one place, and then when you need to move it, you move it to another place. And all of your data and all the rules, right, all the programs that you're running, all the connections that you have with other people, network connections, those can all restart seamlessly when you move it from machine to machine. And you can pass it down to your descendants, is the idea. You own it, it's all yours, nobody can interfere with it. And yeah, it's completely yours, completely sort of autonomous. Now, in order to do that, we have to have a virtual machine. And we want that virtual machine to be as simple as possible for a number of reasons. And the big one is that the more you understand something, the more ownership you can have over it, right? So if there's, Google, so Chromium, for example, right? 20 million lines of C++, right? This is the code base that Google Chrome is based on, right? It's open source. So, theoretically you can fork it, and every once in a while people do, and they make Brave and things like that. But the individual is not really going to understand how Chrome works, not really. Even a programmer is not really going to understand how Chrome works. It's just too big, it's too complicated. And so it's very difficult for an individual to own and maintain and a very complex system and modify it to their liking and keep it up to date and whatever. And so Urbit strives to be as simple as possible, and also just in general because we think it's the right thing to do. Ethically speaking, software should be simple enough that you can know that it works. Really, I think my face just got tiny.
It did. I'm trying to get your darn desktop on there. I'm worried that it's maybe only letting me do one guest at a time.
Yeah, the chat seems to have gone quiet too, so hopefully people are still on there. I'm gonna get a chat echo here if you guys are still there. Great. Okay.
Still here. Okay. Yeah, I don't know why that your desktop is not.
Okay, so this is a great example, actually, right? No one knows why this software isn't working right. And even if Lightstream were open source, there's nothing we could do about it, right? Like, we're just out of luck here. So we really don't want Urbit to be that way. So we want Urbit to be as simple as possible in this whole new world of computing. So one of the big simplifications that you can make in computer programming in general is to use pure mathematical functions as a model for what you're doing. So basically, you can define how the system is supposed to behave by writing out a function, which ideally you can write out in some kind of mathematical notation, and saying that this is, a function from input to output, and that's all that'll ever happen. So the whole field of functional programming is based on this idea. There are a lot of different sort of strains of functional programming within that. And Urbit says, yeah, that's true. That is better. That is simpler if you can swing it. And really, you should do it for the whole operating system. So formally speaking, the state of your Urbit at any given time, the state of this virtual machine, is completely defined, completely specified by the sequence of inputs that machine has received. So an input is something like a key press, or an HTTP request, or a packet from another Urbit, or a timer elapsing, right? Any new piece of information, or even like setting the entropy, right? Setting the bits of randomness can be used for cryptographic operations and other things like that. All those things come in as any new information that comes into the system comes in as an event. So it comes in as an input to this function. And so the way, and this is not a new idea, right? If you think about it, all blockchains also have this property, and databases do something very similar. And so the event log is where we write all those incoming events. So whenever we get an incoming event, so like if I press a key, then that gets written to disk. All right, it gets written to the log, it's appended to the log of all the events that we've gotten. And this is actually sort of all of the persistence that Urbit needs, right? Because once you have this list of events, if you lose your current state, it doesn't matter. You can reconstruct it by just rerunning those events, and you'll get back to the same place because it's a function. Now, it's a there's actually a cultural divide here between computer scientists and mathematicians. When mathematicians talk about functions, they mean a total function, which means that if there's an input, it definitely results in an output. Computer scientists usually mean a partial function. So nock, which is Urbit's transition function, is a partial mathematical function, meaning that every input either results in an output or infinite loops, basically. So if an infinite loops, it never gets to an output. And in fact, we treat this as an error condition, basically, in nock. So that's the way you get a nock error is use infinite loop. And this is actually pretty nice because it means we don't have to define a special error type or anything like that. But in any case, partial function is good enough because if you do get a result, you'll be able to get it again, basically. So there are actually some details there that I'm eliding. Happy to go into that if you're more interested. We actually kind of just figured out how error handling should really work in Urbit just a few months ago in a kind of generic way. So we're in the process of implementing that right now. But the overall idea is really pretty simple. It's that you get an event, you write it to disk, and that sequence of those events can be used to reconstruct the state. And so that way, if you're running and you accidentally spill your cocktail all over your computer, but the hard drive is okay, then you can take that hard drive. It's got all the events on there. You can start up a new. You can restart your Urbit from there. And we also add one optimization to this.
Hang on now. Are we back? It says loading. Right. Something's going on. This I it can't catch up. Now it's going nuts. All right. We back?
Maybe. I mean, I think I'm here. I'm not sure. I'm going to switch to Zoom because this is just not working, man. So I posted a Zoom room.
Okay. Now can Zoom? Yeah, can Zoom?
I think we get. Do you want to just come join in Zoom?
Yeah. All right. Hang on. Zoom. Let's see if I didn't. I don't know if I saw. Where's this? Can you text me the Zoom? And then
I
I'll
put it in the
stop.
chat here.
Okay. My chat is too fast. All right. No, I don't see the Zoom. Oh, isn't that great?
It won't let me post it.
They're blocking. It's blocking the Zoom link. Oh, son of a gun. Well, it seems like it's streaming now.
The Zoom ID. Okay, I can post the ID maybe. Man. That's incredible.
See, that's the problem with these big technology guys. And I'll have to figure out another way to do this next time. Holy cow.
I'm going to do the Zoom meeting ID. Meeting ID. Four 938.
No, I'm not seeing it, Ted. Isn't that interesting? Well, if this should continue to work as long as you don't. I mean, the whole problem was me trying to do the screen share. You know. Oh, there it is. It's 3 parts.
Okay, well, actually, maybe we should just leave it. I mean, if they can hear us now,
let's just because it was me trying to get the desktop sharing working.
Oh, okay. So if we don't touch anything, then it should work still. Because maybe maybe the best thing we're going to get here is audio. And we should just take what we're going to get and not try to switch to Zoom because we'll
probably lose everybody.
Yeah, apparently the Turing cops will get us if we try to leave YouTube. Man, what a Kafka-esque experience. I typed like four different kinds of links into this chat, and none of them worked. It just blotted them out. It didn't even tell me. It didn't say like, no, you're not allowed to post that here. I just posted, and it would let all the other messages go through and not that one. That was weird. Okay.
Next time I'm going to try Twitch, not YouTube.
Yeah, man. Try something else. That was crazy. All right. But we're still good now, right? You can still hear me. You can still see me, or maybe at least hear me. All right. I was trying to talk about Urbit at some point in like a previous life. Yeah. Yeah. Okay. So I was talking about the event log, right? Yeah. All right. So the event log. Yeah. All right. We write the events to disk. Every once in a while, we take a snapshot of the current state, and that snapshot means that all the events before that snapshot, we can keep them or we can throw them out. Because in order to get to the current state, you just have to start from some snapshot and replay all the events from there on, and you're back to the current day, right? And so this is technically called a prevalence system, although I haven't really heard that term used too often. But all the big NoSQL databases, big distributed databases like Google Bigtable and Spanner and all this kind of stuff, and also non-distributed databases, just normal databases like MySQL or Postgres or whatnot, and also some file systems like ZFS use this kind of system where the events come in, you spool them out onto disk, and then periodically you truncate that listing by taking a snapshot. So this is not a new idea, but taking a whole operating system and sticking it into the database is a relatively new idea. And so, because what you have actually, Urbit is this transactional system, right? Like out of this concept, you get a transaction where, if the function runs on an input and gets an output, well, then you've completed a transaction. And if it hasn't gotten that far and this event hasn't been written to disk, then it never happened. All right, so this is also like a database where you get this atomicity, where this event either happened or it didn't. And one part of this that I haven't touched on is that, so we've talked about input to this function, but you also want to get output from the function and have it go back out into the world, right? There's the old Haskell joke that Haskell's has no side effects because no one will ever run it, and so the only, in some deep sense, like the only reason we ever run a computer is for the side effects, or at least the effects, right? When you're talking about pure functions, you usually think of those as side effects, but for us, it's really an effect because the way we get effects out of Urbit is that those are part of the result of running the function. Whenever you run the function meaning the operating system, right? The whole thing's just one function. And so whenever you run that function, it produces a pair. And the head of the pair is a list of effects, and the tail of the pair is a new modified operating system that will then handle the next input. So this is actually self-modifying on every event. Right? And normally we don't replace the code. Right, so normally we just replace parts of the data. It's like, okay, well, we saved a file, we increment an account or whatever. But sometimes we actually do replace the whole thing with a new piece of code, and this is how we how we push down updates over the network. So when we call an OTA, an over-the-air update, like we can just send you a bunch of new source code as some packets, and the system churns on it, compiles it, replaces itself with the newly compiled program, performs a migration from the old program to migrate the state, just like a database migration, and then it's done, and that's your new thing, and then that can just go ahead and handle the next events. So from the perspective of the runtime, right, the program running on Unix that actually runs Urbit, it doesn't even necessarily know that this thing has completely replaced itself with some new program, because it's always replacing itself with some new program. It's just how much of it you're replacing. So this idea of, you can replace yourself with something else, this is a very kind of like old Lisp idea, relates to the concept of homoiconicity, the idea that code is data and data is code. This is actually basically always true, but it's sort of more or less apparent in different systems. It's very apparent in Urbit, specifically because we need to be replacing programs with new programs, and treating programs as data, and then also taking in data and being able to treat that as programs. So being able to convert between those things is actually a fundamental task of system software. And in fact, modern operating systems that are not Urbit, but Unix-based operating systems and Windows, like they do this all the time with machine code. All right, so machine code is also just a bunch of data stored on a disk somewhere, and then you jump into it to run it. Right, so machine code is really also extremely homoiconic, arguably even more homoiconic than Lisp. And so Urbit is sort of actually
There's
a little
no
bit
distinction in
right,
machine code.
or in C, really.
I was an assembler programmer for a while. I mean, they're the same thing. It's all a virus.
Yeah. And actually, I met a guy that worked at Symbolics in the 80s that worked on built the Lisp machines. And when I described Urbit to him, he said, "Oh, I understand what you're doing," which is an uncommon reaction, actually. And he goes, "You guys are making a statically typed Lisp machines." He was like, "That's a great idea," because the problem with Lisp machines was that they were so dynamic and so flexible that you could just make a mess out of them really easily and end up in a bad state. And in fact, this is a big difference between Urbit and a lot of somewhat comparable systems like Loper OS and and maybe the Smalltalk images. I know less about them, but a lot of systems that have this kind of self-mutating property are designed around this kind of like be as flexible as possible, and everything's kind of loosey goosey and do whatever you want. And Urbit's very much not that. I mean, we do intend it to be useful for creative work, so there's a tension there, but
believe it
but
or
actually.
not, I was a Smalltalk guy as
Oh, yeah?
well, and a lot of people don't know this, but Smalltalk had a method on object called become, which let an object become another class on the fly. I mean, that was the ultimate in mutation.
That sounds
You were a
totally
cat,
safe. I
now
can't
you're a
imagine
dog.
anything. I can't imagine anything that could go wrong with that.
Exactly. So yeah, it was pretty flexible.
Yeah. I haven't described this because the type system in Urbit lives at a higher layer, right? So nock, which I'll describe in a minute, which is the thing that the event log uses, and it's the thing that that Unix understands. Nock is dynamically typed, or basically untyped. It's really untyped, I guess. And then Hoon, which is our programming language, which compiles down to nock, that's statically typed. So we actually have a statically typed user-facing programming language that compiles down to this dynamically typed language, or untyped language. And so it's at the untyped layer that we get this kind of, mostly at the untyped layer where we get that kind of self-mutation. Although Hoon's actually pretty good at it too. Much better than most statically typed languages. It's unthinkable to try to do the kinds of metaprogramming kind of stuff that we do in Hoon in Haskell, which is another statically typed functional language, or really any of them that I'm aware of. Okay, that was a bit of a digression. But all right, so we talked about how we have this event log. We periodically take checkpoints. And what happens is that at each event we run some function, which I haven't described what that function is, but we run some function to get from the last version of the OS to the new version of the OS and some effects. So I'm going to attempt to share my screen here, and hopefully the world doesn't explode again.
Yes,
But I'm not going to make any promises here. All right, can you see my screen?
Let's see. I'm going to try to add it to the screen. So I just did add to scene.
Yeah.
And now I'm going to say send to live. It says updating stream.
Okay. All right.
And I can see your screen.
Yeah.
But they can't, I don't think.
Man, this is rough. If only had like a whiteboard.
Yeah, I don't know why it's not.
If only you guys spoke Hoon, I could just speak the Hoon at you. Which is what I would do with,
I
all right.
think.
Oh, I just canceled it because.
Okay. Yeah.
I feel like we've abused our audience enough. I don't think we can. I don't know how much more it'll take before they just start throwing Molotov cocktails at us. Yeah.
Yeah, we'll do better next time, folks.
Okay, so I'll just have to talk with my hands. What I was going to describe to you is nock, and I guess I'll still describe nock to you, but I'll be slightly. I'll have a little bit of aphasia, I guess. So nock is the function that runs. Well, it's actually a language for expressing a function, basically. And what happens is we call that function, we like run that expression in a particular way every time we get an event. So I'll start by defining the data model of all right, so I've talked about, we have these input events that come in, and we have this OS, right? The Arvo OS. And that Arvo OS at any given time is a result of running this sequence of inputs. But I haven't said what those things really are. So I'll describe the data model first, and then I'll describe how nock defines the transition function for how we get from one piece of data to the next piece of data, right? How this thing evolves over time. And then once I describe nock, then I'll also describe how we use nock in Arvo, which I don't know if we've ever really kind of defined that completely, but I'll see if I can actually get there with you guys. Okay, so the data model is what we call a noun. And a noun is it's a recursive data type. It's a binary tree of numbers. And so the way it's defined is you can say it's either an atom, which is a number, and it's a natural number that can be arbitrarily big. So either 0 or bigger, and there's no limit on how high it can be. So that's an atom. Or it can be a cell, and a cell is a pair of nouns. So this is why it's a recursive data type, right? A noun is either atom or pair of noun. So it refers to itself. And so the simplest tree is just an atom. So all these are trees, right? Any noun is a tree, and it has bifurcation points. And so any tree that's made up of bifurcations where at the leaves you have numbers, that's a valid noun. So the simplest one is just one atom, right? So the number 0, that's a valid noun. The number 130, whatever, is a valid noun. And then because it's this arbitrarily large number, you can actually treat it as a buffer or like a string, right? So you can actually just have a string of text, represented as like one big binary number. And in fact, we do this a lot. And we have a 128-bit date format. There we go. And that's also encoded as an atom. and a bunch of other stuff. So anyway, but it's just kind of like representing one atomic piece of data, right? Something that's not divisible. That's what atom means, right? You can't divide it. So that's an atom, or you have a cell, right? So a cell is a pair, so you have some structure, right? So anytime you want to represent structure, like if you where you might want to have a C struct or a linked list. A linked list is a tree that looks like this, and then like this, and then like this, and then like this, and like this, right? So it like grows down and to the right, terminating in the atom 0, which we use as null. So we can do a null terminated linked list. If you guys are familiar with Lisp at all, the reason this is called atom and cell, those terms actually come from Lisp. So nock is actually very similar to Lisps. There are many Lisps, many languages in the Lisp family. Nock is in some sense a distillation of a lot of Lisp concepts, with a couple of major differences. But this overall data model is very Lispy. And it's enough to embed all kinds of stuff, right? So you can embed all kinds of things in atoms. You can embed, lists in as, these trees that grow downward and to the right. As I said, we can also embed maps and sets and queues and all kinds of other things. And they get log n performance, good enough for most stuff. Because they're these recursively defined trees. So we basically embed all these other data structures inside of nouns. And so the whole world of Urbit computing, all that you ever get is a noun. So every input event is a noun. The state of your computer at any given time is a noun. Right? When we take a snapshot of a noun. And a program running at any given time within that computer is also a noun. A file is a noun. Everything's a noun. In Unix, everything's a file. In Urbit, everything's a noun, basically, right? It's a very different idea because it's this like concrete tree. It's like, this is the tree. That's it. It's not moving. There are no special properties. There are no special data types. There's nothing sort of hidden. It's just this mathematical structure. And you're not allowed to know anything about its memory representation, right? So like from inside of nock, you can't check whether two trees are actually like at the same, at the same address in RAM. Most Lisps you can do this, but if you can do that, then it violates this idea of like all you need to understand nock or to implement nock is just the concept of an ordered pair and the concept of a natural number, right? A number that's greater than or equal to 0. So we actually adhere very strictly to that, completely. That's it. And it's also, so this gives us this very concrete representation of all the different pieces of this machine, right? It's always just a noun. And then so the one missing thing that we need is a way to say, okay, well, if your operating system is just this noun, and you get an input that's a noun, how do you take those two things and actually, treat them as a program, right? So what we do is not only do we embed lists and dates and all these other things, not only do we embed those into nouns, but we also embed programs into nouns. And the way we embed a program into a noun, that's nock, right? So nock is a specification for how to treat a noun as a program. And in particular, it's treated as a pure functional program. All right, so it's a partial function and it's Turing complete. So it can be used to represent anything that you might want a computer to do. And you can find the spec online. Famously, to us at least, the nock spec fits on a T-shirt, and we have such T-shirts.
I've got one.
All right, good. Do you have nock 5K or nock 4K?
I read the first one, whatever the first one was.
That's nock 5K. Yeah.
Okay.
Hold on to it. You never know.
Yeah.
That's a collector's item. So I say 5K and 4K because nock version numbers decrement down to 0, at which point we will never update it again. So we're currently at version 4. We have 4 more chances to change nock, and then that's it. So because we want it to freeze and become a standard. And this is true of actually all of the Urbit kernel, but not the
It's
runtime.
only changed once in the last 4 years, I guess. So
Yeah, that's right. Yeah, and it's fine, really. So the way it works, the way nock works, is it looks at it's always a nock expression is always has two parts: subject and a formula. The subject, I really wish I had a screen for this, but subject, it's okay. The subject is basically the argument, and the formula is the function. And in fact, you can think of it. It's mathematically correct to think of the result of a nock expression being the result of running the formula as a function of the subject as an argument. But the way it normally works is that you actually encode the whole environment, the whole scope. So sort of like everything that you want to refer to in your program, that's generally in the subject. So the subject is like the environment, the context in other languages. So usually the subject actually includes the whole standard library and lots of functions that you can run, like not just pieces of data, but also other functions. So if you want to call some other function from the function that you're in, generally that other function will be in the subject. So we call this subject-oriented programming. It's a bit of an unusual way to do it. And it's a little bit like object-oriented programming, but not very much. And it's sort of embedded in this pure functional paradigm. It's also similar to the state monad, if you're familiar with that in functional programming, very similar to that, where sort of everything comes with this implicit state, essentially. It's also a little bit similar to Forth, the old programming language, where there's a stack, an implicit stack, and you're always modifying that with every operation. The Forth stack is very similar to the subject. So there are a lot of kind of parallels between this and other things, but there's nothing exactly like it. So this is the overall structure of a nock computation. You have subject and formula, and you run the formula against the subject. And there are about 12 opcodes. There's about 12 different instructions that you can ask nock to do. So nock 0 says grab a subtree. All right, so it's either like grab the whole tree, which is the identity operation, or you can say grab the head. It's a cell, right? Or you can say grab the tail of the cell, or you can say grab the head of the head, or the tail of the head, or the head of the tail, or the tail of the tail, right? Etc. And we have a little numbering scheme. So, head of the head is 4, tail of the head is 5, head of the tail is 6, tail of the tail is 7, etc. That's nock 0. So that's take a subtree. All right. So if you run 0, 1 on any subject, it'll just produce that subject unchanged. If you run 0, 2 against the subject, that'll produce the head of that subject. So that's nock 0. The next one is nock 1. Nock 1 says ignore the subject, just produce a constant. So 1, 17 will always produce 17 no matter which subject you run it against. Nock 2 is metaprogramming, and this is in fact the only kind of basic control flow construct that we have. So we build if and function composition and our sort of what we call our function calling convention. We build those out of nock 2, or we could at least. And what nock 2 says is you take the formula looks like 2 CD. Or 2 BC, let's say, because the subject is usually A. So we have 2 BC, and we say run B on A to get the new subject, run C on A to get the new formula, and then run nock on the new subject and new formula. So the other way of thinking about this is it says construct a new computation and run it. This is actually corresponds, so nock 1 corresponds to the K combinator in the lambda calculus. Nock 2 corresponds to the S combinator in the lambda calculus. And nock 2 also corresponds to Lisp's apply functions. It's function application. You're saying, run this code to get a function, run this code to get an argument, run the function on the argument. That's nock 2. So basically, all the control flow constructs, like all the ways of sort of controlling what this, making decisions in a program, all that kind of stuff, that all relies on metaprogramming in nock, and therefore also in Hoon, which compiles down to nock. So that's nock 2. There are 12 opcodes. I'm going to go through them. So nock 3 is check whether it's an atom or a cell. So it says run something against the subject that produces something else. Take the result of that and look. And if it's a cell, produce 0, and if it's an atom, produce 1, or maybe it's the other way around, whatever. But anyway, it's a way of checking. So you can use that to inspect any noun and look at the structure. Nock 4 is increment. So, and nock 5 is check equality. Nock 4 and 5 are the only arithmetic operations in nock. That and nock 2 for looping is enough to rebuild all of math. This is a sort of well-established result. It's isomorphic to the lambda calculus results from, there's a long sort of mathematical tradition of this going back to like Alonzo Church in the 30s, maybe even the late 20s. I mean, it goes back a long time. So we do, in fact, rebuild all the basic arithmetic out of these constructs, but we don't run them in that way because that would be too slow even for us. So we have a special way of dealing with that called jets, which I can talk about later. But anyway, nock 4 is increment. So it says, take a formula, run it against the subject, that gets a result. That result had better be an atom, add 1 to the atom. Nock 5 says, it's 5 BC. So it says run B on A, that's the head. Run C on A, that's the tail. Check whether those are two equal trees, right? Are the trees the same? And equality in nock means, are the two trees the same shape, and are all the leaves numerically equal? That's actually all you need to get to Turing completeness. That and nock autocons, which is a bit of a strange word. Cons is the Lisp term for make a cell. And so if you have a pair of formulas, a cell of formulas, then the nock will run the head formula against the subject. That'll form the head of the result. It'll run the tail formula of the subject. It'll run the tail formula against the subject. It'll produce, and then that'll produce the tail of the result. And so it just runs the two of them in parallel. So you have, head gets run against subject, produces the head. Tail gets run against subject, produces the tail. That's the result. So that's autocons. So the combination, and that's how we actually produce a pair, is that we just have one formula to produce the head, another formula to produce the tail. So the combination of those is enough to get to Turing completeness. But we also have a bunch of other ones that are basically for convenience and for establishing the standard of how nock actually gets used by languages that'll compile down to it, namely Hoon. So nock 6 is if then else. So it has 3 subformulas. The first one gets run against the subject to check whether it produces 0 or 1. And depending on which one it produces, it'll either run the first formula or the second formula. And it's a short-circuiting if, so it doesn't have to run both sides. It'll only run the one that's actually, that actually needs to get run. Nock 7, it takes 2 subformulas, runs the first against the subject, produces the result, takes the second one, runs it against that one, gets the result of that. So it's function composition. Yeah. Nock 8 is declare a variable. So what it does is it takes 2 formulas. First, it takes the first formula, runs it against the subject, takes the result of that and sticks it in the head of the subject. So it prepends it to the subject, makes a new subject that consists of a pair of this new result and the original subject. So we've basically taken some computation and stored the result in basically a variable and stuck that variable in the head of stuck it in front of the head of the subject so that now it's in scope. So this is why we call it declaring a variable. And in Hoon, the tis-faz and tis-less runes compile down to a nock 8. And so then once we have this new augmented subject, we run the second formula against that to produce the result. So it's like a let or a with clause. It's like, with this thing equal to this, run the rest of this, and keeping all the rest of it in scope. So that's nock 8. Nock 9 is our calling convention, which relies on the concept of a core. And this is actually going to be crucial for understanding how Arvo works. So it's like, how do we actually process an event that uses nock 9? And so what nock 9 says is it's basically a way of running a stored formula. So if we're storing a formula somewhere in the subject, then what the nock 9 says, okay, take the formula that's at this place in the subject, pull it out, and run it against the whole subject. And really, it says actually, like, run some formula first that produces what's called a core. Now, nock doesn't actually know exactly what a core is, but this nock 9 basically constrains you to using something like a core for expressing sort of a combination of code and data. So that's what a core is, really. It's a combination of code and data. We can use it to represent, it's like a lambda with an implicit fixed point. If you're into that sort of thing. It's also, it's a way of representing something that's a lot like an OOP object, like in object-oriented programming. It's also a way of representing a library, an anonymous function, just a recursion point. It's a very kind of generic way of representing some code and some data bundled together. And the way it works is it says, produce a core. So nock 9, the way it works is it says, run something against the subject to produce a core. This core is going to be, it's going to have a stored a formula somewhere in it. Somewhere in its tree, it's going to have a formula, like a literal formula. And then grab the formula out of the tree and then run the formula against the whole subject that was the result of running that initial computation. Right? So it's like, run some computation that gets a core, and then pull up one particular formula out of the core and run it against the whole core as the subject. Seems a little weird, but the reason to do this is to get that implicit fixed point, right? Because most of the time you want to be able to loop. You want to be able to recurse. And in order to recurse, you actually have to have your actual definition sitting there in the subject somewhere, because that's the only way to refer to it, right? It's not like in Haskell where the compiler just does some magic for you, and it's like, oh yeah, well, all functions can refer to themselves, of course, because that's how we designed it. It's like, no, you actually have to have it in the tree. You have to have a tree somewhere. Like, you have to have something to refer to. So this is a pattern for how you can do, and mathematically this corresponds to what's called mu recursion, or a fixed point recursion. And so this is how we do that in Hoon. It's also very similar to a De Bruijn index, if you're familiar with that encoding of lambda calculus. So often the other thing we can do is mutual recursion. So this is why it's useful for a library, right? If you have a bunch of different functions that need to call each other, then you can actually have the shape of a core is a pair of code and data. Like, it's like too dumb for words, right? It's like, how do you encode code and data? It's like, well, you have a pair, you have the code and you have your data. The code is a tree of formulas. So it might just be one formula, or it might be a whole tree of formulas in different places. And so if you want to do mutual recursion, then you put a bunch of formulas in the tree, and then they can all call each other through nock 9, because they're all calling back into the same core as the subject. And if you want to do a loop where you're updating some counter, right? Like, let's say you're writing the decrement function in the slow way, then you're going to need to track some counter, right? Because the way you do it is you start from 0. You want to decrement n, right? So you want to subtract 1 from n. You start from 0, and then you keep adding 1 using nock 4 to 0. And then each time you check equality. Say, well, if I add 1 to n, if I add 1 to my counter, let's call it c, right? If I add 1 to c, is that equal to n? All right, so like when you start at 0, it's like, well, if I add 1 to 0, is it equal to n? Say n is 3. It's like, well, if I add 1 to 1, is it 3? No. If I add 1 to 2, is it 3? Yes. Okay, then we're done, right? So then we can return 2. But in order to do this, we actually have to have this counter, c, and n. Those have to be in our subject, right? Because they have to be in the tree so that we have them in scope, so that we can access them. And so there's a pattern for this, where the data portion of a core has 2 segments. So the data portion of the core is itself a pair, and it's too dumb for words, right? And the so the head of that pair is the argument to the function, n. And then the tail of that pair is all the other sort of pieces of the environment. So it's usually the standard library, whatever else this function was sort of defined against, right? Whatever environment was there. Hoon is a lexically scoped language, so it's actually just whatever was in lexical scope at the time that this function was defined. That's really nice. Old Lisps were dynamically scoped, and people got really crazy with it. Lexical scoping is nice and sane. Right, so in this decrement example, you're going to want n, the number that you're trying to decrement. You'll put that as the sample, which is the head of that pair. So that's the argument. We call that slot, we call it the sample. And then you're going to want to put c, this counter, somewhere in the context portion, right? The tail of the tail of the data portion. So the and then basically whenever you recurse, right, whenever you call back into the core using nock 9, you first edit part of the core. So you change C to be C+1, right, by incrementing it using nock 4. So you run a nock 4, you swap out that part of the core, and that's the last operation in nock that has semantic meaning, which is nock 10, which says take a tree, take some particular part of it, and replace it with the result of running this other computation. So that's edit. So it's like take a tree and edit a piece of it.
Now it's physically, it's a completely new tree though, right? Like you don't ever actually edit.
Yeah, this is a subtle point. So logically speaking, nock tree is always completely immutable. And all you can ever do is create a new nock tree. Now in practice, there are 3 exceptions to this in the current interpreter. It's up to the interpreter how to make exceptions to this, if any. But one is structural sharing. So when you have a subtree, it's actually just a pointer in memory.
Okay.
In our current implementation and most implementations. And so it just points at the subtree. And so if you have other trees that subtree is a part of, then they'll all typically point to that same subtree. And this is called structural sharing, right? So we have a reference counted memory system, and so it tracks how many things are pointing at it. And if it goes to 0, then we free the memory. But what's nice about that is that we actually pass logically. It sort of blurs the distinction between pass by value and pass by reference, right? Which are normally 2 different ways of. So just a decision to make in programming languages, basically. And for us, we always logically pass by value. You're always just passing the whole tree, but you just pass a pointer to the tree. With an exception, actually, that if it's a 31-bit or smaller number, then we just pass it directly by value. So that's it's because we have a couple bits at the front of each memory cell tagging what it is. So if it's just a little number, then just go ahead and copy. That way you don't have to do a pointer chase, right, and uses less memory. This is a pretty common technique for runtimes, but yeah, you do that. Okay, so that was one exception, right? It's structural sharing, where you're actually modifying the reference count, right? So that's not strictly immutable because the reference count number changes. There's a 4th exception. Another one is that we lazily calculate a short hash. So there's a slot in there that might or might not be filled with the hash. It's an insecure hash. It's just used for internally in the interpreter for optimizations. So then there are 2 more exceptions. The third one is that we occasionally unify nouns. So we defragment sometimes. So we'll say here are 2 different trees, but they're actually equal, but they're not in the same part of memory. So then go and find all the references, delete one of them, take all the references to that and move them over to point at the other one. So that's unification. We do that periodically in a defragmentation phase. And we also do it when we do certain kinds of equality checks. And the fourth one is an optimization, a memory optimization, where if the ref count is 1 and you do an edit operation.
Then you actually change it.
Yeah, because nothing else cares about it, right? So it might as well just modify it in place. So that's the set of deviations from purely immutable data structures. Logically, in nock, like from when you're a nock programmer, there's still immutable data structures. But what happens is you're creating this, like as you run a computation, right? The runtime will allocate all these new nouns that are the like modified versions of the subject, right, in a stack as you like call different things, right? So that's what you're actually doing is it's allocating all these new subjects in the heap that are slightly modified from the previous one, and most of them share structures. So you're basically like, it's just like when you modify the sample, you're creating all these different, slightly modified versions that mostly point back at the original. Unless there's only one reference count, in which case you're just mutating it in place.
Okay.
Yeah, it's a good question. So to pop the stack one, I was talking about nock 9. And the so that we so typically as you're iterating, right, as you're looping or recursing, you'll be editing the sample. You can actually edit any part of the subject at any time. And so actually when we're doing decrement's a good example here, where like you're actually editing part of the context. Like the end, the argument to what you're trying to decrement, that stays the same as you loop. You're just incrementing a counter, right? And so it's the counter that gets edited. So that's going to be like the tail of the, sorry, it's going to be you're going to go tail, head. And that's going to be where you're going to find that, right? Because tail is going to be the standard library. Tail, head is where you're going to find the counter. Yeah. So that's what you're going to increment when you recurse and decrement, depending on how you implement it. So that's the function calling convention, right? You have all this stuff in scope, including some functions. So pick out one of those functions and call it against this whole thing, against the whole core as a subject. And in general, like the way we call a standard library function, like decrement, or the way you like load a function, like the way you kind of retrieve a function and then call it with an argument, is actually not really fully specified by nock 9. But what we always do is we do a nock 9 and a nock 10 to edit. So what we say is all functions actually start with a default argument. So, like the default argument to add is a pair of 0 and 0. And so what you do to call it with some argument is you first you grab the core, which by running a subtree, right? You like find a subtree of the subject, basically. Right, somewhere in the standard library. So you dig it out, right? And you've got the core that has add and all these other things. And once you have add, then you take the sample, which is normally 0 and 0, and you swap it out with 2 and 3. And then you say run the only formula that's in that core. We call it an arm, right? So we know that there's only one formula there, and it's the like run the add function formula. And so the procedure is grab the actual add core, swap out the sample with 2 and 3, the actual argument, and then run the formula that's in there against that modified core. So that is what we do when a new event comes in. There's a slot in Arvo in the tree. It's a sample slot. It's just a sample, actually. And we take that slot, or is it a sample? Yeah, it is. So we take that slot, and we replace the value of that slot with the actual event that came in. And then we fire the arm. It's the poke arm of the Arvo core. So there's there are a few different things you can do with the Arvo core. It's not a gate. It's not like add where there's only one thing you can do. There are actually a few different operations that you can perform on it. There's poke, peek, wish, load, and come, I believe. So poke is the one where it's like we're running an event. So it's like, here's an input event, deal with it, produce a pair of list of effects and new version of yourself. That's poke. You can also peek, which performs a lookup. You can give it a path. So do you have anything at this path? And you can do a wish, which says run some Hoon code against yourself or against your standard library. That's a sort of stateless thing, almost. And then load is the runtime saying, hey, replace yourself with this new source code, which we do sometimes for diagnostics or for like recovery if something goes wrong. So that's how it actually works, right? New event comes in. Let's say you get a key press, right, through some like Linux interrupt, right? And somehow Linux delivers you this information. It's like, here, you pressed J. Then the Urbit runtime transforms that into a noun that says it's basically like a pair of constant saying I'm a key press, and then a numeric representation J. Yeah, like that's it. And it takes that and it sticks it into the slot in Arvo that says here's where the input goes. Sticks it in there and then just runs the poke arm of Arvo. So it runs a nock 9 of Arvo, and then the Arvo var interface, right? The interface between Arvo and the runtime. Part of that specification is what are the locations in the Arvo subject, like where in the tree can these different formulas be found? And there are 4 or 5 of them, and so those are just hard coded. And so you can then because they're hard coded, actually, then it's a very mild optimization there too, where the runtime can just come right in and just poke the thing it wants. So the last operation in nock is nock 11, which is a hint. So this has no semantic effect. Like basically what a hint says is emit some information to the runtime, and then run this other formula against the subject. So it'll run, and there are actually 2 parts to it. There's a static hint that we never use, and there's a dynamic hint, which is the one we actually use. The dynamic hint actually has 2 parts. It has a constant, just I think an atom actually, which is just a tag saying this is this kind of a hint. And so the runtime can look at that tag without running anything else and say, like, do I want to run this hint or not? Based on what that tag is. So let's say it's a printing hint, right? We have a bunch of those. So some runtimes say like, oh, I'm not going to bother printing this. I don't feel like it. So it'll just go ahead and run the formula without running the hint formula. But if it does decide to do the print, then what it'll do is there are 2 sub-formulas, right? There's one that produces the actual hint to the runtime, and there's the one that produces the semantic result that the rest of the computation cares about. And so if the runtime decides to actually run this hint formula, then it'll run it, look at the result, maybe print it or do something with it, throw it away, and then produce the result of running the second formula. And that's it. That's nock. Those are all of the opcodes. This fits on a t-shirt. And that's how we actually run Arvo, right? Like, that's the entirety of it. We use nock 9 and nock 10 for editing part of a core. And the big constraint, going back, zooming out a little bit to kind of wrap this up a bit. We remember this. The state of your Arvo at any given time is a pure function of all of the input events that have happened up until then. And the rule and each one of those events is a transaction. So it's atomic. It either happened or it didn't happen. And so the rule is that when a new event comes in, we try to run Arvo on it. If that fails, then we don't bother writing the event to disk. What we actually do is then we look at the stack trace that came out of that, and we create a new event saying, hey, this thing that never happened failed because of this reason, and we inject that in as an event and run that. That's new information, right? So one rule to keep in mind when thinking about Urbit is that the only way that new information can ever enter the system is through a new event, right? So it's like you can't find out about your stack trace until the runtime injects it for you, if it's a non-deterministic stack trace. Which some of them are. So but it's transactional, right? So this either happens or it doesn't happen. So if we run Arvo on the event and it does complete and produces effects and a new Arvo, then we write the event to disk. And once we're sure that that's been written to disk, then we can take the effects and actually go and perform them, right? And we meaning the runtime here, right? So var, the program that you're running on Linux OS or Mac OS that's actually executing Urbit for you. That will look at the effects, which might be like, hey, like draw a J character to the terminal, or like send an HTTP request to somewhere, or send a UDP packet to another Urbit. There are 5 I/O channels for Urbit. So there's and so it can only be one of those things, or a bunch of stuff for communicating just between Arvo and var. Just kind of life cycle stuff, like, hey, I just restarted, here's like this IO driver rebooted, stuff like that. But it's very isolated from the host OS. And that's part of how we kind of keep it pure and keep it in this sort of crystalline form that's going to last a long time.
Yeah, that's what makes it so easy to move from, you can bundle it up and move it from a Mac to a Unix and it doesn't even care.
Exactly, yeah. Actually, that's how I've deployed some. We're doing some ops, like because it runs faster on my laptop than it does on most cloud servers, and so sometimes if I have to boot up a lot of ships, if we're doing a big deployment, then like I'll sometimes I'll just boot them up on my laptop, tar it up, SCP it up to the cloud, untar it and run it there, and it's a little faster, and it just works. It's useful. And that's switching from Mac OS to Linux, and it just works seamlessly.
Yeah, it's pretty neat. It's pretty neat. Do you want to see if there's any questions on the chat?
If any of you are still awake.
Yeah, if there's anybody still listening, if you want to type in a question on the chat, we'll see if we can see it and answer it. Uh-oh.
Maybe later.
There were a lot of people on the stream. I mean, I hope we haven't lost them.
Yeah, I hope so too.
It says it's still going. Oh, here we go. Okay, no question here.
Oh, great. Okay.
To talk. All right.
Cool.
We'll wait a moment or two. Anybody?
I guess I should probably mention that Urbit does have a system called Jets. So, this is not how the runtime actually runs decrement. It has a function that's written in C that compiled down to machine code that uses the processor's ALU to run decrement. It's one of the nice things about having concrete. It's one of the reasons that nock has such a concrete representation of functions, anonymous functions, and closures. So a function that has a piece of data wrapped up in it. The reason that all those things are represented so concretely is so that the runtime can look at them and say, oh, I know how to run this, and run a faster version of that. So this is really what makes nock just a specification for a computation, and not just like a lot of things claim, like, oh, it's just an executable specification, but no, like we often execute those specs in a different way by running a jet. So there's a little bit of overhead with actually doing the matching and finding a jet. Doing the matching and saying, like, how do we know whether this nock code is actually jettable, right? How do we know whether it's valid? because you don't want to let some crappy code you installed like try to violate that. So the system has to be robust against that as a security concern. And but we cache the crap out of this basically. So we have this sort of like recursive matching scheme. It's a little bit complicated, but it makes it so that we can cache a lot of the basically memoize a lot of these jet matching validation operations. And there's a guy, Fodwit Ragful or Fraudwith on GitHub, who he's working on like revamping that system and optimizing it more so that it's and the trick there is really to store a pointer to the jet like in the actual noun. Right, so there's a trick there where like you store that particular noun specially so that we can do it quickly. This is runtime work. I don't know too much about how that works exactly, but anyway, it's like he's doing that work. It's already not that bad, but there's actually a lot of optimization there to bring that can like we can bring that function call time down a lot.
Right. Yeah. Well, I always figured that my philosophy has always been you don't want to spend too much time optimizing up front because you don't really know what you need to optimize until you really use the system, right? And at this point, there's so many more important things than Urbit being super, super fast.
Yeah.
So.
Absolutely. Yeah. I mean, it's fast enough for most of the things we want to do with it. Loading the chat page is usually like under a second.
Yeah.
I mean, it could be faster, but it's fine. It's faster than Keybase. It used to be a little slower than Keybase, but these days it's faster. Still, some things are slow. Over-the-air updates are slow. The compiler is slow. There's sometimes key lag in Dojo. That's I don't know. Yeah. There wasn't a year ago, and then something happened. It got a little slower, so we're gonna have to go in and fix that again. But it's like you're right that we have a lot of like very specific performance problems, but like the performance of Urbit as a whole, like as a system, is actually fine. It's totally fine. Yeah.
And to me, it's much more important that it be clean, right? Like because for me as I was talking about to me at this late stage in my career, why Urbit is so exciting to me is because it's almost it's a chance to go back and build the stack the way it should have been built with all of the things we've learned since the 60s, right? Like the problem with our current systems is they are literally just slag layered upon slag of crap on top of crap. And if you ever spend 10 seconds in the world of JavaScript and things, I don't know. I mean, I'm like, I
spent years in the world of
Java. I want to shoot myself. Like when and it's so funny because those are the times when I personally almost want to despair, right? Because I'm old enough to remember about when we were just so frustrated because, LS worked a little bit different on AIX than it did on HPUX, and everybody was pulling out their hair. And then it was like, oh man, the internet and the World Wide Web and it's going to save us and all this stuff, right? And now I'm in a world where I wish I could have the days of incompatibilities between Unixes, right? Like now is a modern programmer trying to deliver a program on the web, and I can have like this is legit. I used to work at a fairly big e-commerce website, and a update to Chrome can totally break your website.
Oh yeah, definitely.
And to me, that's like, now I'm having to track what version of Chrome do you have on what device, on in what mode are you in landscape mode? Oh,
and this is right. And this problem is actually so difficult that if I recall, when I was doing web development, there were like competing strategies on how to deal with the incompatibilities.
Yeah.
And the strategy that was winning at the time when I was doing this a few years ago was that you actually didn't even bother to ask what version of what browser it was. You would just try to do the thing that you wanted to do and see if it worked. And if it worked, then you say, okay, well, I know this works. But you would try that for every different thing that could possibly vary between browsers.
Yeah.
Right? You just try it. And that was the best you could do.
Now they're just going back to the old strategy, which is,
oh,
oh, sorry, I don't work in your browser, right?
Oh,
Google Hangouts doesn't work in Safari.
And I didn't know
Safari.
that.
I mean, that's a pretty big platform, right?
Yeah, it's arguably anti-competitive, right? Like,
yeah. So that's what. So
you
that's
could probably make an
always tell.
antitrust argument there, right? Like, it's like, hey, this is supposed to be like a browser. You're supposed to just like implement the standard, like.
Well, and browsers can black screen your computer now. Chrome black screened my Mac the other day. I mean,
Wait, what does that mean?
Oh, it crashed my Mac.
Like, really?
Have you ever not got it? You've never gotten a black screen where it just says, you get a black screen and it says, oh, your computer's going to restart in a couple of seconds.
No.
And then it comes back with I really only started getting a lot of them with Catalina. Have you not upgraded to Catalina?
No, I'm wait, which one am I on?
Do it.
Don't upgrade to Catalina. I'm on High Sierra 10.13.
Oh, I'm on 10.15.
Yeah, it's because I know that like there's a bunch of build systems that broke on.
Yes, and they changed
on later Mac OS.
they changed the file system, and apparently in some kind of a significant way. And I guess what they're trying to say, right? And this is the lamest excuse, but because I brought my profile forward, right?
Yeah.
From it's another one of these. These are what these companies say, right? Well, if you had just installed from a completely clean install, you wouldn't have any of these problems. But it's like, dude, I'm not going to reinstall everything, right? And repave but they changed something in the way the file system works. So they've got a lot of problems because of it, I guess. Yeah. And Chrome, because after you black screen, it comes back and it says, you want to send your report to Apple. And if you're people like us, you can read these things and you can kind of figure, oh, what app crashed, right? And it was Chrome. It's like, oh, so great. Chrome can crash the entire OS now.
Yeah, well, it figures in some way. I mean, because Chrome has had to recapitulate most parts of an operating system.
Yeah.
Itself, like in its own code base.
They are OS now.
Yeah, pretty much, right? Like, this is, I think, part of why they had the idea of a Chromebook. They were like, well, we've got this thing. It's like kind of like an operating system already. Could we just use that as the operating system? The answer is like, yeah, kind of.
They don't use the printing system of Mac anymore. I mean,
right. Yeah. Oh, they don't use the same. They don't use the same, like, I think they have their own graphics stuff. They have their own process sandboxing. They have their own task manager. It's like, how is this not an operating system kernel? Like, what? And it's actually, I think it should be something of an embarrassment for actual operating system kernels that Chrome had to rebuild all this crap on top of them. It's like, you guys should have solved this. Like the needs of a modern application, like.
But that's why I say
the Urbit landscape is in JavaScript.
Keep it clean.
Yeah. Philip on the chat. Isn't the Urbit landscape the Urbit UI? Isn't that in JavaScript? It sure is. You should hear our internal discussions about this.
I'm one of the ones who's not all that happy about it, but I'm willing to go with it for now.
Yeah, I mean it's the shortest path from A to B, basically. Yeah. One thing we've talked about considerably, Little Panas, who's a Talon employee, has some very. He actually has a lot of experience with browsers and graphics development and compositing, all this stuff, and. So he has some very in-depth ideas about like what an Urbit-based browser would look like, and what and just sort of overall UI paradigm, so it's both like So it's both, a bunch of ideas about like what the layout system should more or less look like, what the application system should more or less look like. He modeled it pretty closely after Elm, the front end system. And then what the database layer should look like, which probably look more like Datomic, something sort of similar to that.
Yeah.
And then
that's a really interesting system too.
Yeah, very similar to Urbit in a lot of ways. It's a referentially transparent database, right? So like, a lot of similarities. But there's a it's one of those projects. It's like it's like a tenth of Urbit, right? Like, there are a lot of these, but I guess what's so interesting, I think, about Little Panos's vision for this is that it's very data oriented. So we really shouldn't be sending down code most of the time. Really, it's actually pretty rare that we interact with some new website that requires an interaction paradigm that's so different that we should actually like install code on our machines. Almost all of it should be data.
Right.
And a lot of the reason that's done is just for branding purposes, basically, because you can't really style a website with just CSS. You actually need the JavaScript, right? So you got to send down that code at least. But then also, even all the styling and all that kind of stuff is mostly there for branding. And so if you're designing a system that's focused on personal computing, where like kind of propagating the branding stuff is not really the point. And like what you really want is just a data feed. It's like, I'd like to just subscribe to your data feed to see what you're telling me. And like, actually, I want to style that myself. I don't want to look at it the way you want me to look at it.
I don't care how you want to style it.
Yeah.
Right? And the original web was a lot like that as well.
Right. Yeah. Like, that's part of the idea of CSS, right? Is that you should be able to have your own style sheet. Wasn't that in there at some point?
Yes.
Like, you can still do this in
at the
browsers.
very beginning. Yeah.
It's like, it's sort of technically in there still, but it's one of those sort of vestigial features, like running an email server. It's like, yeah, you can run an email server. It's like, you're not going to. If you do, nobody will listen to you, but like, you can.
Has he ever seen Squeak? Are you familiar with Squeak?
Remind me what that is. I'm not sure if I know.
Smalltalk, but it had its own UI and windowing, like built in as part of this.
No, I'm not familiar with it.
But it was exactly similar to what you're saying. Like, it's just based upon drawing pictures and not all the code stuff.
Well, so actually, how does Urbit compare to the Smalltalk images?
It's similar in that Smalltalk images are the same kind of like the static, like the snapshot, right? Like everything is live, and if you stop it and you come back, it's exactly where you left it. Like it was just like in hibernation.
But they didn't have an event log based system, did they?
If the more industrial strength ones basically did, like Gemstone, that were meant to be run like on a server. Yeah, they did.
But that wasn't kind of, so there's no real way to run Urbit as anything other than an event log.
Right.
Because we're a single level store. I mean, this is something I didn't really mention during the description, but like, if you don't do anything weird, then like this whole system that I've described, just what falls out is a single level store where basically like all the data that you care about that you're tracking, like that's in your system, logically lives in RAM. And like maybe it gets spooled out onto disk for swap if you run out of RAM, but that's opaque to you from inside the system. It's just like there's data there. There's no like read a file and there's no write a file.
Right.
So like we have the system called Clay inside of Urbit that we sometimes call a file system because it maps from path to data. But that's like the only way in which it's a file system, and like in all the other things that you think about with file systems, it's not that. So arguably, we shouldn't even call it that. People give us crap about like making up names for stuff, but then we try to use existing names like, oh, this is a file system. It's like, no, it's not. This is not a file system. Like, there's not an inode in Clay.
Right, or try to put something at the root. Try to make just a folder. You can't.
Right. Yeah, that too. Yeah, it's just
Right.
different model.
Yeah.
But so anyway, so Urbit's a single level store. Were the Smalltalk images single level stores, or I would imagine that
Yeah.
they were.
I mean, you could access the file system, but you'd have to pull it into the image.
Okay, but the image would have. I'm assuming here that the image would actually have multiple pieces. There would be it would have its own file system inside of it that you could read and write to, and that was what would be persisted, and then everything else would not be persisted. So you'd have more flexibility, where it's you could decide whether or not you wanted to persist something or whether you wanted to keep it as a piece of transient state.
No.
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 So it was a single store.
Yeah, I believe so.
Interesting. So that's a little bit more
Yeah,
similar to Urbit.
there wasn't a concept. I mean, you could access a file, you could access a database, but you couldn't. When you saved it in objects, it was saved in the image. Every object was live in the image.
Okay. Interesting.
Yeah. And you could inspect everything, and you could change them on the fly as well. I mean,
so why do you think Smalltalk didn't catch on? What were the problems with it?
It was slow compared to other, and it was hard to understand, right? I still remember. So I had been coding when I first looked at Smalltalk. I had been coding for probably 15 years, and I had been a professional coder, full-time professional coder for more than 5 years.
Okay.
I had done assembler and C mainly.
Right.
I actually learned Smalltalk in Palo Alto at Xerox PARC from the original Smalltalk guys.
Huh.
And
Alan Kay and all those guys?
Yeah. I know cool. Ron Jeffries and some of those guys, Kent Beck. I have never felt dumber in my life, right? I literally, so I did 2 weeks in Palo Alto, and I came back and I couldn't get a program to run. You know what I mean? I was in class, I was cool, and then I came back and now I'm gonna work, and I'm gonna be a professional Smalltalk programmer. I couldn't get anything to work. What was hard about it? So different. It was so different. There is nothing but objects. There's nothing. If you can't, there is no main, right? There's nothing other than classes and methods. So until you sort of make that mental shift, right? Even everything about it works the opposite as other languages, right? So in C, I essentially start with nothing, and then I want, I want to be able to do I/O. So I need to import I/O basically, right? So now I bring I/O in, right? And then, I want to print. So I got to bring in a print, you know what I mean? So you kind of cobble things together from nothing, right?
And you basically just stick them together in the file, right? It's all transclusion.
Smalltalk inverts that, right?
Okay.
Smalltalk, you start with everything.
Yeah.
You have the image. You've got the whole enchilada, right? And then you make your program, you get your objects to do what you want them to do, right? And then you strip everything else away down into your program, which is only the things that you need to make your program work. And then the Kickstarter thing that starts your image going, right? So it's that whole inversion of, but in some ways the subject feels like that, kind of, right?
Yeah, I mean, it does have everything in it. Well, I mean, not everything. It has the standard library, but in Hoon, because it's all just a pointer, you don't bother getting rid of stuff out of the standard library. Who cares?
Yeah.
It's just a pointer to the thing that's there that everything can point to. So we don't actually,
Yeah, I think that was more optimization.
Okay, yeah,
because it
but
was big and slow, to have everything.
okay, interesting. Yeah, I mean, I guess they didn't have structural sharing, probably. I
Yeah.
would imagine
And in
it's
the
harder to
90s,
structurally. I mean, a dynamically loaded library, right, or like to structurally share code if you're not doing, you know,
right.
uh, this sort of like if the basic data type isn't structurally shared,
Right.
right, which it is for us, which is unusual. Um,
Yeah.
Although I don't know how they stored Smalltalk objects, but I wouldn't imagine. I
I
mean, they were all mutable, right? So like, I wouldn't imagine that they were working on like functional data structures for that. No.
no. Like I told you before, everything was mutable. And I mean,
Yeah,
you could rewrite methods on the fly if you wanted to.
right. Yeah, I have a friend who complains about this with Emacs, that like that you can just kind of like reach into it and like twist around like all the basic functions, and like you can just break it really easily, and there's no like way to ensure that if you install multiple plugins that they actually compose properly.
Right. It,
That's like the kind of problem you would get with a Smalltalk image based on the way you're describing it.
Yeah, yeah. Now it was super productive and cool because, for example, I mean, unit testing started in Smalltalk, right? And the
Oh, right,
coolest
yeah.
thing, and it's hard to explain how this worked, but you would run your unit tests in Smalltalk, right? And then if they hit an error, they would break, right? And it would
Yeah.
stop. And what you do is you would just change the code and then resume. You could even pop back up the stack a couple of stack frames, change the code,
Yeah,
and then resume and go. And then that's
I
all you
see.
did. It was like you were just constant, like
You jump
debugging.
up the
You
stack
never
frames. Oh
stopped.
man,
Yes. Oh, that was
that's like
amazing.
too much. That's too much power, I think. Like I remember,
Yeah,
like you
you
can
could
do
see
this
the
in.
variables change on the stack frame.
It's one of those things that's like, in Python you can do this too, actually, right? Like in Python you can do get
Yeah.
stack frame, and it was funny that I worked at a Python shop for a few years. We were doing robotics, and some distributed system stuff, and it was we would run the Python. Sometimes we would run it on Linux for like processing servers, and then we would also run it on Windows to run the hardware, right, to run the actual robots, and just all the drivers were for Windows, and most things worked okay. Right, it's Python, right? It's a virtual machine. You should be able to run it anywhere, right?
No.
But when you start looking at the stack frames, they look a little different. Uh,
Yeah.
And in general, it was like the only reason we ever looked at the stack frames was actually to just make it a little bit more convenient to do logging, because it would like look. We had this thing that would like hook into the like loader basically, so it would look at like, hey, what file are we loading, or something like that. I don't remember the details, but I remember it was part of that, and it's just so that we didn't have to like have a line at the beginning of every file that was like logger equals logger of underscore underscore file underscore underscore, right? Like, and just
Yeah.
to avoid that line, we looked at the stack frame. Terrible decision. Absolutely terrible decision. We should just had this stupid line. Like, who cares? But you have to learn these things by experiencing them. And it was just, and then you get the craziest errors come out of this, right? Like, because you just, like, it's like, I don't know, you're trying to take a jog and you just like punch out your kidney. It's like, what goes wrong? I don't know. Like,
Yeah.
something's
Once
going to
you're
go
there,
wrong.
you're in deep. You're in deep. You're in the
Yeah.
that movie Inception,
Yeah.
right?
Right. There's an interesting thing about Urbit where, like, as kind of unusual as it is in so many respects, it's extremely conservative in other respects, right? It's like it's like a very strict stack discipline, right? Like structured
Right.
programming. Like, you don't have exceptions. Um, we don't have call CC. Um,
Yeah, that's one of the things it's very compelling about it. It's so once again, to me, I would describe that as clean. It's very, it's like there's not there's not a lot of ways to hurt yourself.
Yeah, there aren't too many
like there
foot
are in
guns.
some of the other languages and OSs, right? There's just so many ways that, you know. So and there's kind of, so that's what I like it on both levels, right? You've got the on sort of the landscape side, you've got that we're building an OS for people, not marketing machines,
Yeah,
right? To sell people.
right.
So you've got the cleanliness and the beauty there, and then it's matched with the underlying system that's clean and beautiful, that will allow that system to stay clean over time, right? It's
Yeah,
a nice house built on a good foundation.
yeah. I
So,
think that's a very good way of describing it. That's definitely what we're trying to do. So it's nice to hear it. It's nice to hear it from someone that isn't just the back of my head.
any other questions in the chat? I know we've kind of gone a little wild. It does say that there's still 30 people watching, if you can believe it.
Wow, good stamina. I'm
Yeah.
impressed.
Yeah. And I'm pretty sure that YouTube saves this, so this will be available for replay, technical glitches and all. I promise to practice and be better at this if I ever do this again. Maybe Twitch will stream better. I don't know why I couldn't stream your desktop. I got to get an answer for that, because it says right here that I'm supposed to be able to have 4 channels, right? Like it's telling me right now I'm using 2 out of 4. And then your thing was popping up, but every time I said add to scene, it wouldn't show up. So
You said you've been programming since 1977?
Yes.
Maybe after another 43 years, you'll figure out how to do video chat.
I'm usually pretty good at this kind of stuff for an old guy. I mean, I've been doing this.
No, I like it's. This is not a critique of you. This is a critique of the system, right? I mean,
yeah.
That reminds me of something Paul Graham once wrote about. That like somebody asked him, like, is it useful to have a PhD in computer science? And he said, well, my mom asked me to fix her thermostat, and I read the manual and I tried to fix it, and I couldn't figure it out how to use it. And so, yeah, it is useful to have a PhD in computer science, because I can say, I have a PhD in computer science and I can't figure this thing out. This thing sucks.
Yeah. I know. Computers do weird ass things. I don't know if you saw, I was asking on the Urbit room because I still can't figure this out. But my wife's laptop, a MacBook Air, all of a sudden stopped being able to communicate to the device on .6 on our local network. And I have no idea why. And it's not the device. I know for sure, because she found it out because she couldn't print, right? Okay. So I shut down. I finally figured out, like, oh man, she can't talk to .6, right? Which was the printer at the time. So I shut down all the devices, shut down the network. I booted everything back up. So the printer came back up on .8, and now she can print. My cell phone's on .6, and she can't ping my cell phone now. So she can't communicate on the local network. And I've been asking everybody, is there anything in Mac that you can set us? And she does not have an outbound firewall that I know of on .6. And it just started.
Yeah, it's hard to know, you know. I mean, it reminds me of, I know I have a friend who used to work at VMware. And so she said that she would work with some chips, and they were like, you know, they're doing a lot of low level work on various processors, and at some point they were doing a bunch of like big distributed testing of some kind, you know, brute force kind of testing, and some tests were failing, and so they did this like very complicated correlation, and you know, and figured out like, okay, why is it this cohort that's failing here, and they kind of narrowed it down, and they eventually figured out that there was a processor implementation of SHA-256, and there was a bug in it. And so under very certain circumstances, it would just get the wrong answer, calculate the wrong hash for something. And so they were only able to find this very large scale.
Yeah, and there's still there's stuff like that. Who knows? So it keeps it fun, I guess.
Something like that. I mean, I really do hope that that we can keep Urbit small enough. I'm confident that we can. We're making it smaller. We've made it smaller since I've been there. Past 2.5 years or so. And I think there are a couple other shrinkages that will happen soon. But it really are there are just so many. I mean, I worry a little bit that it is hard for people to wrap their heads around Urbit, and we're trying to make it easier, but it's still tough for people. But there's something where the learning curve with Urbit ends at some point. It stops. Yeah. You're like, oh, okay, that's it. That's Urbit. It's just there's no more to this. Whereas it's really not the case with the rest of computing. And so when you compare what it is that Urbit does and then how much you have to learn to do that, it's the ratio of how much you have to learn for each component of it is so much tinier than all right, we'll try to learn IP and TCP, and then it's actually what about IPsec and DNSSEC, and what about they're actually 4 or 5, well, more than that, different congestion control algorithms for TCP, and then they're well, actually this TCP implementation runs in hardware and has these different and well, and then there's NATs, and then they're you have to do stun and turn. Well, actually, stun and turn, if you read the RFC, they're provably insecure.
Well, right.
Man, that was a moment for me. Reading the RFC for, was it stun or turn? It's one of them, and it's it has this big disclaimer at the top. It's it is not possible using cryptographic means to make this secure. And I was this is what everybody uses. This is what the internet runs on. Right? And
but I mean, and I know people will say I'm I'm just an old curmudgeon or whatever, but I'm not unconvinced that we're heading to some weird the system to me is showing early signs of gridlocking up, right? So I just recently went, and I'm in another startup because I'm not really a big company guy, but I was running an IT department at a relatively large company before I left. And one of the last straws that I was I can't take this anymore was I had to start fighting the battle. My corporate IT management wanted me to stop allowing my developers the ability to install software on their own computers.
Interesting.
Right? They wanted them completely locked down. So a developer's not even an admin on his own laptop. And if you want to install Python, right, you now we're going to have to put in a ticket to IT, who would then, some dude would walk to your desktop and install Python for you, because he'd have the admin password, which you wouldn't have.
Yeah.
Right. Because they are just losing the battle against the nefarious forces that
the forces of entropy, basically, right?
Yeah, with the current.
These things are so fragile, you can't withstand a tiny deviation. It's well, if you have Python in this machine, maybe just having installed it will break our other stuff.
Right. And there's so many bad actors out there, and they just need a little seam. And none of these OSs are, because back to my earlier point, that they're just crap piled upon crap piled upon crap. Nobody even knows are these. I mean, there's another security alert coming out against these every minute.
Yeah.
It's so I don't know. I mean,
It's only
you
the
know,
past couple of years I've realized just how porous all this stuff is.
yeah,
You know, I
yeah,
thought it was like a stack made of like a stack of bricks. It's really more like a a stack of pumice stones or something, or like a
yeah.
stack of styrofoam bricks. Like or Jenga. It's more like a Jenga tower. It's like,
Well,
yeah,
it
let's
is,
yank.
and then
Can we yank this one out? Huh?
right, and it just stops working, and it just stops working. It's going to be interesting. It's going to be interesting to see what happens over the next years. But I hope that Urbit is going to be just at the right time. You know what I mean? It's just,
Yeah,
and people will say, "Hey, if I can go to this, if landscape is getting, you know, close enough that if you had a good hosting strategy, if you could give this to somebody, an a la Chromebook,
yeah,
and I mean, I think it's still maybe a year or two away, but it is, you could see where it's going now. And
yeah.
and I've
It's
always
much
felt
easier to
like
see than a
the
couple of
the,
years ago.
the killer app is going to be, or the killer thing is along those lines you were talking about, of simplicity, to build distributed applications easily, because even
Yeah.
today building a truly live distributed app
Oh,
is not with current tools.
it's
So
highly non-trivial. Yeah, definitely.
but Urbit by definition should make it easy. I
It
mean,
makes it a
it's
lot
kind of,
easier. I mean, like,
yeah,
you have a totally like you have a real identity system. You have all the like um all the encryption and authentications handled for you. All the serialization, deserialization is handled for you. All the persistence is handled for you. The total ordering on messages is handled for you.
right, which is
That's a
not
huge
easy.
deal.
Oh my God, it's a huge deal.
It's such a
I mean,
pain
I've
trying
built a lot
to.
of messaging systems on Tibco, and exactly once delivery is frickin' hard.
Yeah, yeah. It's
Yeah.
like it's something that you should build into the base layer so that people can use it because you don't want everybody to have to rewrite that stuff. Um, so
Yeah. All right,
yeah,
man. Well, I've taken up enough of your evening.
yeah, it was great
We'll
talking to you. Thanks for
why don't
having
we
me
cut it?
on.
Yeah, thanks.
I'd
Hopefully we'll
love to
see you
learn more
tomorrow.
about actually some of the other stuff you've worked on in the past at some point in a future date, I guess.
Cool.
But yeah, like I've never met any other small talk programmers. So I mean, among other things. But yeah, it's so that was really interesting. Thanks for filling me in on this stuff.
Oh, yeah, no worries. And yeah, we'll get you up here maybe once the quarantine is
That would be
lifted,
great. Yeah, I'd love to come
and
visit.
we'll take you out and have a good time.
Yeah, sounds
So
great.
thanks again. Thanks for everybody for watching. Appreciate it. Hopefully you got some good information out of this. And Philly people, I don't know exactly what we're doing next month, but we're doing something the last Tuesday of every month.
All
So
right, sounds
thanks.
good.
Thanks, guys. See ya.
Have a good night.